Okay, in this video we're going to do a few odd problems from 5-2 growth and decay section there in calculus. And here's a nice slow pitch right over to plate. Number one. Let's read the directions first. It just says solve the differential equation. So the first thing we want to do is separate our variables. Notice here on the right we have our x's, and then on the left is a dy dx. Now whenever we see this, always at least mentally put a set of parentheses around this. The right side here is a quantity, and we're going to multiply both sides by dx now. So the dx is outside the parenthesis, and then it applies to both terms inside. So now I got my dy on the left. We're going to integrate both sides. So if we antiderive here on the left, the antiderivative of 1 with respect to y is y. And then here we got two terms. We'll do each term separately. So here's x to the first. We could raise the power by 1 and divide by the new power. And then here's a 3. Antiderive that with respect to x. That'll be a 3x. And then add our constant to this side. Remember, we'd have a constant on both. Combine them into one constant. And now that I look at this, there's another way to antiderive that. We looked at each term in the parenthesis as a separate, so we could antiderive it just like that. Let me leave this answer here, because I'm going to try it a different way, and hopefully the two methods have the same answer. So now if I look at this as an inner function u, the derivative of that inner function would just be 1 dx, and I have a 1 dx. So this is to the first power. So I could, kind of u sub this and get y equals. I would take my quantity, raise the power by 1, divide by the new power, and then add on my plus c. Now the question is, are these two answers equivalent? I think so. So let's see here. Let's do a little algebra on the red one. So let's see, I got a half here. I'm going to keep my half out. And then if I FOIL this out, x plus 3 quantity squared will be an x squared plus a 6x plus a 9. And then here at the end I got my plus c. Now if we distribute, the 1/2 hits the x squared. There's a half x squared. Half hits the 6x. Half of 6x is 3x. And then half of 9 is 4.5. But we got an unknown constant there. 4.5 plus our unknown constant is just another unknown constant. So that one, there was two ways to get to the answer. Number 3. Now, look at this over here. On the right, on number 1, we had an x plus 3. Now it's y plus 3. So to separate the variables will be a little different animal. Of course, we're going to multiply both sides by the dx. Now it's over here. Now, as a quantity, we're going to divide both sides by y plus 3. So now we have dy over y plus 3 is equal to dx. And now we're going to antiderive each side. So here, this is y prime over y, or u prime over u. So this is going to become natural log absolute of y plus 3. And then on the other side, we'll antiderive the 1 with respect to x and get an x plus c. Now, to really solve these, we want to get y by itself. So right now, y is in natural log there. So we got to bust them out. Oops. And how do we get rid of natural log? With the base e. We're going to exponentiate each side. So over here, e to the natural log will cancel, and we've got our y plus 3. Now over here, we're going to have e, this is one big exponent, to the x plus c exponent. Think back to the proof we did of y equals ce to the kt. Here we are adding exponents. When do we add exponents? It's when we multiply the same base. So I could make this term an e to the c, and now we're multiplied. E to the x times e to the c. And remember, e is just an irrational number, and we can have e to exponent c is just going to turn into another constant. So this will turn into one big constant that I can put in front. C e to the x. And now to get y by itself, let's subtract the 3. C e to the x minus 3. And one more to go on this slide, number 7. Okay, first let's get rid of that prime notation. Time for a little Leibniz, dy dx equals. And I'm going to rewrite the root of x as x to the half, and then times y. Okay, let's start separating the variables. Multiply both sides by dx. Now the dx is on this side. So there's our x and our dx. Let's divide by y. So over here on the left, dy over y. That's looking like natural log. And then here we got x to the half dx. Okay, left side, dy over y. That's a natural log of y. And then over here, x to the half, we're going to raise that power by 1 to the 3 halves. And divide by the new power 3 halves, bring it up, flip and multiply, 2/3. And then over here, we'll put on our plus c. Now, just like the last one, to get rid of this natural log here. And when we base it, remember, e to a positive exponent is going to be positive in the first two quadrants. So we can drop the bars here, and we'll have y equals. Now, when we base e this side, we got, remember, this is one big exponent. So since we're adding these exponents, this now becomes a times e to the c, and that e to the c is just going to turn into a constant, and we'll put that constant here in the front. C 2/3 x to the 3 halves power. And this is getting a little messy. We'll get that out of the way. Oops, hold on there. Yeah, when when my constant come back here, it doesn't take the place of that e. What was I thinking? We're going to have a c e to the get back there, 2/3 x to the 3 halves power. There it is. There we go. So y equals c, e to the 2/3 x to the 3 halves power plus c. All right, number 11. Ooh, now this is a word problem here. Write and solve differential equation that models the verbal statement. The rate of change of q with respect to t is inversely proportional to the square of t. Okay, let's dissect this with our English skills. The rate of change sounds like a derivative. Rate of change of q with respect to t. So rate of change of q respect to t, dq dt is, translates to equals, inversely proportional. Okay, let's just think about the proportional part. That means we're going to multiply what's ever over here by some constant of proportionality, k. Now, when it says inversely, remember that means we sort of flip it over. So if it was proportional to the square of t, we would multiply this by t squared. But since it's inversely proportional, it's going to be 1 over t squared. All right, so there is our equation that models our verbal statement up here, our written statement. Rate of change of q with respect to t is proportional to the inverse of t squared. Okay, this doesn't look like it's going to be too bad. Let's separate our variables. We're going to multiply both sides by dt. So now that winds up on the other side. And yeah, remember k is just a constant, so t's and dt's are separated. Just for a quick rewrite, I'm going to get rid of that t squared in the denominator, bring it up and make it a t to the negative 2 power. And now it looks like we're ready to antiderive each side. And remember, with k being a constant, we can just factor it out in front of the integral and then put it back. So the antiderivative of 1 dq is q equals. Now here we're going to raise our exponent by 1, divide by the new exponent, and then we still have this as just multiplied by that constant k. And we'll put our plus c on this side. So let's get rid of the negative exponents. Q equals. So let's see, we're going to have a negative in that term. T to the negative 1 is going to drop to the denominator where it becomes t to the first. We can just put that k upstairs and put our plus c on there. All right. Number 15. 15 is a red problem. If you're getting sick of listening to me, you can always get on CalcView and check out that one. But it says here, find a particular solution. Find the function y equals f of t passing through the given point. So there's our point, 0, 10. With the given first derivative, graphing utility to verify. This will be a piece of cake. One step to separate our variables. Multiply both sides by the dt. Now it's over here. So anti-derived dy, we get a y equals. So here that's a t to the first. We're going to raise our power by 1 up to squared and divide by the new power, so it'll be over 2. And we'll put our plus c on this side. And then just to clean it up, 1/2 times t squared over 2 is t squared over 4. And we've got our plus c. So there is the general solution. General solutions have a plus c on them. And now in the directions, they gave us the point 0, 10. So we're going to use that point to find the particular solution. So y is 10, and that's going to equal t is 0, 0 squared over 4 plus c. This term, 0 divided by anything is 0, so that's just gone. And we see that c is equal to 10. So I can just take my general solution here and erase that plus c that was there and put on a plus 10. There's our particular. Number 19. Okay, this is one of our y equals ce to the kt problems. It is a red one, so you can check out CalcView if you want. But it says here the rate of change of n is proportional to n. So this gives us the permission to use y equals ce to the kt. Remember, this is our formula with the calculus baked in. ce to the kt. Okay, when t is 0, n is 250, so they did give us a point, 0, 250. And t is 1, n is 400, so we do have a second point. What is the value of n when t is 4? So they did give us 1, 400. And our end game is finding 4, question mark. Okay, so I've written the formula out once here. Let's plug in our given values. Y is 250 equals c e to the 0k. 0 times anything is 0. E to the 0 is 1. So c is equal to 250. So now we have another point. Here's t. Here's n, and now we have c is 250. So let's plug those into the formula again. So this y turns into a 400 equals this c is now 250. And then we have e to the k times 1. K times 1. Or I'll just write it as k. There we go. So we can now solve this for k. Step 1, divide by 250. So we get 400 over 250. Let's just make that a decimal. 1.6 is equal to e to the k. And now to get rid of that base e, we're going to natural log both sides. So on the left here, natural log of 1.6 is equal to the ln of e to the k is just k. So our k value is just the natural log of 1.6. So we can write our equation as y equals 250 ln of 1.6 times t. And now we can use that equation to solve for the y value or the n value here when we make t into a 4. So we would just replace this t here with a 4 and punch that into the calculator. You're going to get approximately 1,638.4. Or if you keep it in the form of a fraction, 8,192 fifths. Okay, I think we got 2 more to go. Similar to this, 21 and 23. 21's the easier variety. We do have the time 0 initial condition, and then we have another point to solve for k. 23 is one of the harder varieties, like that last example in the notes. So the directions are simple. Find the exponential function, passes through to given points. Here they give us permission we're allowed to use y equals ce to the kt. So let's see, I'm just going to get our points here. So we're going to use 0, 2 to solve for c, and then 4, 3 to solve for k. And then here they're not asking us to find any given point out farther on the line. So this should be getting pretty routine. This, when we solve it, c is just going to equal 2, because if we do y equals c e to the k times t, 0, k is 0, e to the 0 is 1, c is equal to 2. So we've got c is equal to 2, and we've got another point for our x and y, or excuse me, t and y. So y equals c e to the k, oops, write it like this, k times t will be 4k. All right, let's get the e by itself, divide by 2. 3 halves, I'll leave it as a fraction. 3 halves equals e to the 4k. Take the natural log of both sides. So here you'll get that to cancel, and you'll just have the over here on the right side 4k. So we're going to divide by 4. Y equals the natural log of 3 halves divided by 4. And let's turn that into a decimal. So that is approximately 0.1014. 0.1014. So our final answer, final equation, y equals 2e to the point 1014t. Okay, easy ones out of the way. Let's do the trickier one. So we have 2 points, but sadly, neither of them is the time 0. So here it's kind of backwards. The last one we solved for c first. It was nice and simple. Used that c to solve for k. Here it has to sort of go in reverse. Let's use our first point. Y equals c e to the, at least here it's nice it's a 1. K times 1 is just k. Now to get c by itself, we're going to divide by e to the k. And an easier way to write that, 5 over e to the k, let's bring it up and negate the exponent. So now it's 5e to the negative k. And now we're going to use that over here. So this is going to take the place of the c value. So here's y equals c, that's our 5e to the negative k. So there's our y equals c e to the kt. So this will be a 5 times k. 5k. So on the right here, we can simplify. We have a 5. Multiplying the same bases, add the exponents. 5k minus 1k is 4k. E to the 4k. Let's divide by 5. 2/5 equals e to the 4k. Of course, next step is going to be to natural log both sides. Oops. So the natural log of 2/5 equals 4k, and divide by 4. K equals natural log of 2/5 divided by 4. And let's get that as a decimal. Approximately negative 0.2291. 0.2291. So we've got our k value, and now we'll go back and solve for c. Now for this, we can use either point. I'm going to use the one with the smaller values in it, the first point. So here now we've got our t, we've got our y, and now we've got our k value. So y equals c e to the k, that's our negative 0.2291 times t, which would just be a 1 times 1. So we don't even really have to write it on there. Oops. There we go. And now let's solve for c. So we're going to divide each side by this with the negative exponent. So over here it's e to the negative 0.2291. To make it easier for our calculations, let's just move that up and change the exponent to positive. So c equals 5e to the negative 0.2291. And if we punch that in our calculator, we get approximately 6.2873. 6.2873. So now we found our k first. Here we just found the c value. So let's write our final answer. Y equals c, but now that's 6.2873. E to the negative 0.2291t. 2291t. There we go. A little harder to get there. Our answer, I don't think, looks as nice. Lots of decimals in it, each to 4 places. But there we go.